Today we're going to talk about imaginary numbers, and we're going to introduce that with a little bit of geometry review from transformations. So imaginary numbers, a lot of students ask me, if they're imaginary, why do we have to study them? Can't we just imagine they don't exist? But the thing is that sometimes we have equations that can't be solved by traditional methods, so we need to introduce this new number so that now we can solve any and all polynomial equations. So we'll start with a quick review. If we look at each of these exercises in the opening, we can see that all of them have solutions, right? And then even this one, which we know is x squared minus 1, you could factor by difference of perfect squares and then get your two solutions. Or you could extract square roots, right? X squared equals 1, square root of each side. So x is equal to positive or negative 1. So either way, you're able to find two solutions since it's a quadratic. Now, if we get to this one, we have no way of factoring because it's x squared plus 1. And if we use the extracting square roots technique, we get x squared equals negative 1. We solve by taking the square root of each side. And right now, until today, we didn't have any way of dealing with the square root of negative 1. We would just say, whoops, no real solutions, right? Or if we had done the quadratic formula and we had gotten a negative before today, we would have said, oh, I did something wrong. Something must have happened with my mathematical procedure. After today, however, you will have to make sure that you're just being really careful in your work so that you know if the answer is correct with a negative under it or if you made a mistake. So we'll be able to determine that. And we'll talk about different techniques for determining whether or not solutions are real. Okay, so let's take a quick review about geometry. What transformation is the same as multiplying by negative 1? And so for all of the former geometry students, right, if we have a transformation that's the same as multiplying by negative 1, that's like a rotation of 180, okay? So let's say we had some point A, which has coordinates 1, 2. If we rotate it 180 degrees, we end up at A prime, which has the coordinates negative 1, negative 2. So that should hopefully look familiar from geometry. Now let's take a look here, and it says, is there some number that we can multiply by that corresponds to a 90-degree rotation? And if you think back to your geometry, you know there's not really any number that corresponds to a 90-degree rotation. And so this is where the imaginary numbers come in. We're going to imagine that some number exists, okay? So we could imagine that if I multiplied to get here, it would be some imaginary value I, okay? So on the next page, if you flip, you'll notice there's some blank space, and we're gonna fill that blank space in with some information related to this correspondence. Okay, so let's say that we have typical coordinate axes, right? And we have some points on this axis, which are, 1, 2, you could even go out to 3. And now we were looking to find, is there some value that corresponds to a 90-degree rotation? And we said there isn't really one that exists. So we imagined that one exists, and we would have that imaginary value I, okay? So when we get to this value here on the y-axis, this would be 1 times I, or 1I, okay? And we could do the same thing for 2. If I imagine that same thing, just like we did with that coordinate point on the first example there, I have 2 times I, so this corresponds to 2I. Okay? And then we could do the same thing for 3. Now, what if I wanted to get back or do a second 90-degree rotation, which would bring me 180? So I would go, what would take me to here? Another 90 degree. That would be times another I. So I'd have this I times I, and that would bring me back to this point, which we already know to be -1. Okay, and then the same would be true for 2. If I multiply that, I would get 2i squared, or 2 times -1, which brings us to -2. Okay. And then what if I wanted to go another 90-degree rotation? So I wanted to get down to this point, which we know would be another rotation here. So that means I'd have I times the I for the 90 there, and then times the I for there. So I'd have really like 3 I's, I to the 3rd. Okay, and we know that's technically here -1 times I, so this corresponds to the point -1I. Okay, and then if I went one more, that would be -1I times I, and bring me back to 1. Okay, and so that would be like 4 rotations. And so 4 is important because after the 4 is when the pattern starts repeating itself. So we have some values. We have I to the 1st power, which would be I. That would be like that first rotation. We have I to the 2nd power, which would be like I. We know that to be equal to -1. The 3rd one brings us to -I, and then one more time brings us back to 1. And then after that, it would kind of repeat its pattern. So I to the 5th would bring me back to I to the 6th would bring me back, and so forth. So that means that when you get to the problem set tomorrow in class, that you are not going to express any of your solutions except as I, -1, -I, or 1. So sometimes you'll see I to the 23rd power. You can't express that. You have to rewrite it or simplify it. Okay. And I'll talk tomorrow in class about a little clock method that some people use to remember it. It has to do with this idea of rotations and where you end up, but it's sort of a shortcut method, so I'll talk about that tomorrow. So if we think about what we just did here, when we perform 2 90-degree rotations, that's the same as a rotation of 180 degrees, right? Multiplying by I twice results in the same rotation as multiplying by -1, and so therefore we can conclude that I squared is equal to -1, and that's important. Okay, so you want to kind of note that. Now, why might this new number I be useful? Well, remember that first example in the opening, we couldn't really get solutions. But now we have, x squared equals -1. We took the square root of each side. And so then we have x is equal to positive or negative square root of -1, or positive or negative I. Okay, so if I squared is -1, that means that I is equal to the square root of -1. Okay, so now if we take a look at a problem like this, we have a quadratic, and we know that quadratics we solve by either factoring, completing the square, or quadratic formula. And so in this particular case, there are no factors of 5 that add up to 2. So I need one of my alternate methods. I need either completing the square or quadratic formula, and it's really a matter of your preference. Based on the activities in class over the past couple of days with completing the square to deal with parabolas, I'm going to review that method. So with completing the square, we need to make sure we have a perfect square trinomial, and our first step is usually to isolate the variables. So we move the constant over. So now I have x squared plus 2x equals -5. And you know that I usually always leave a blank space because I know that I want to make a perfect square trinomial. And a perfect square trinomial, as a reminder, means that you have 2 identical binomial factors. So what am I going to add to here? I'm going to put a 1, right? Because 1 plus 1 would give me 2, and 1 times 1 gives me 1. On this side, I'm also going to do that. I'm going to add that same thing. And then I have a perfect square trinomial, meaning it has 2 factors that are the same. And then on this side, I'll just combine my like terms. Now, if this was a couple of weeks ago, we would have said, uh-oh, I did something wrong. Now this is perfectly legitimate and fine as an answer. So I'm going to finish solving by extracting square roots. Take the square root of each side. I have x plus 1 on this side. Now remember, it's a quadratic. Quadratics have 2 solutions. So I have plus or minus radical negative 4. Okay. When you have a negative under the radical, we know that that could be broken down to radical 4, radical negative 1. And so we already know the square root of 4 to be 2. So we have plus or minus 2i. Okay, and then one last step. We're going to move that 1 over. And so now I have x equals negative 1 plus or minus 2i. And that would be our solution for a quadratic that's not factorable and that has what we would call imaginary or complex solutions. Okay, the last thing I want to talk about is the fact that you can graph complex numbers, and you would graph them in what they call the Argand plane, and it looks very similar to the regular XY plane. So you would go ahead and draw your axes, and we're just going to rename our axes. So complex numbers are in the form a plus bi, where a represents the real part and the imaginary part is represented by the bi. So this becomes our a-axis, or sometimes it's listed as real, so it depends on what textbooks and who's talking about it, but you have your real axis, and then you have your imaginary, or your I-axis. So y becomes I, if that's an easy way to remember. Okay, and then you can graph those numbers on here. So we have this, let's use that solution from our previous. We have negative 1 plus 2i. Okay, so negative 1 would go in the negative unit direction up 2. And so that would be the point that corresponds to negative 1 plus 2i. And generally, these are graphed as vectors. So you would put like a little arrow like that going to the point, and that would represent negative 1 plus 2i. So it's almost like you can think about this as being like a coordinate point, negative 1, 2i, and that's how you would graph it, and then you just need to have your little vector representing it. Okay, well, what else can we do with complex numbers? Complex numbers can be added, they can be subtracted, they can be multiplied. Okay, so we add them in the same way that we would add, 3 plus 4x and 7 minus 20x. You would just combine your like terms. Okay, in this case, our like terms would be 4i and 20i. And of course, you have your other like terms, which would be the 3 and the 7. So your real parts get combined, your imaginary parts get combined. So we have 10 plus negative 16i, and so we'll just write that as 10 minus 16i. Okay, now the nice thing is the calculator can check these for you, and we'll talk about that tomorrow in class. Okay, so I am going to ask that you try example 2 and example 3 for tomorrow. This one is subtraction, so just don't forget you're still doing all of the same things you're familiar with, distribution of your negatives and then combining the like terms. With multiplication, just remember you do have to simplify those i's, so we can't leave any i's to a power other than 1. All right, I will see you all tomorrow.